Welcome to today's lecture on protection circuits. Today, we will explore the various protection mechanisms used in superconducting magnets. Here's an outline of today's lecture. Self-protecting magnet, passive protection, and active protection. We will cover each type of protection circuit, discussing their principles, applications, and significance in superconducting systems. First, let's talk about self-protecting magnets. These magnets can protect themselves without relying on any external intervention. The key requirement for a self-protecting magnet is that the normal zone propagation velocity must be fast. This means that the NZP time must be shorter than the current decay time, ensuring that all stored energy is dissipated within the magnet, preventing damage. Next, we have passive protection using shunt resistors. Shunt resistors are placed at each coil and are commonly used in persistent mode superconducting magnets. The figure on the left shows a schematic explanation of this protection method. When a quench happens in coil 1, the current flowing through coil 1 decreases, while the current through coil 2 increases due to the flux conservation. Eventually, the total voltage reaches the power supply maximum voltage and the currents start to decay. The graph on the right clearly shows the effect of the passive protection. This slide shows an example of a passive protection circuit for an NMR magnet. The resistance values of the shunt resistors are determined based on the inductances of each magnet. This ensures that the energy is effectively dissipated, maintaining the stability of the system during a quench. Now, let's look at active protection, specifically the detect and dump method. This method transfers most of the stored energy into a dump resistor located outside the cryostat. It involves detecting the quench voltage, and sometimes a bridge circuit is used. When a quench is detected, the switch opens and the current will flow through the dump resistor, dissipating the energy in it. While effective, this method may not work for persistent mode magnets due to the slow PCS open delay. To summarize, a self-protecting magnet dissipates energy quickly across the entire magnet, preventing significant temperature rises. Passive protection uses a resistor connected in parallel with the magnet inside the cooling environment to draw out energy during a quench. Active protection uses a resistor connected outside the cooling environment, involving quench voltage detection and energy dissipation in a dump resistor. Choosing the appropriate protection method is crucial to avoid the burnout of superconducting magnets during a quench.